Hi students, Mr. Wheeler here. Today we're going to learn about geologic history and fossil evidence. Um, so Earth is believed to be formed about 4.6 billion years ago, and roughly half a billion years ago was when the crust formed. So gravity pulled the densest elements to the center of the planet, and then the solid crust formed on that surface. The atmosphere at this time was likely made up of gases expelled by volcanoes, so water vapor, carbon dioxide, sulfur dioxide, carbon monoxide, molecular nitrogen, and hydrogen. One gas that was absent at this time was oxygen. So oxygen didn't show up, or isn't believed to show up for much later, as it's going to be produced by photosynthesizers. Minerals in the oldest known rocks suggest that the early atmosphere had no oxygen. We're going to be talking about some fossil types. So we could categorize fossils by how they're formed or what's left. And so the first type of fossil is going to be a trace fossil. So trace fossils are just that. They are the trace remnants of prior life. The other type of fossil, which is a type of fossil that is most prominent in our area of northwest Pennsylvania, are molds and casts. And so we could see a lot of brachiopod fossils in our area, the small little seashells. And this picture shows some molds and casts of trilobites. The next type of fossil is a replacement fossil. This is when the organic material is covered with sediment, and then over time, metamorphic processes replace the carbon and the silicon in the organic specimen, or rather the carbon is replaced by silicon in the organic specimen, and it's going to be mineralized. It's going to form crystals of a mineral, and so that's a replacement fossil. Permineralized or petrified fossils, they're pretty much the same thing as replacement fossils, except for these are just going to be more crystalline in nature, and some of them are very convincing. I have a sample of petrified wood. It looks like wood. You wouldn't really know it wasn't wood until you went and grabbed it and found it was a rock. The next type of fossil is an amber fossil. This is when sap from a tree landed on, or if an animal touched the sap, it would get stuck and then eventually covered and then preserved for the rest of time, pretty much, since sap becomes amber when it mineralizes. And so many types of insects, and even in some cases some small birds, have been preserved in amber. And then the last type of fossil is an original material fossil, where we actually have the original organism and their organic components are still preserved. And this is usually through processes of freezing or other types of mummification, like in acidic bogs and things like that. So draw all the different fossil types. The way that most fossils are going to form is that the organism is going to first die, and then once the organism dies, it's going to be covered with sediment. Over time, more layers will be covered, and then the sample gets compressed, and then oftentimes it's going to be permineralized, and then millions of years later, erosion has happened, and then thus revealing the fossil. The conditions for fossil formation are very specific and unlikely to happen, and so most things will not be fossilized. And there are some species that are more fossilized than others due to the conditions and the time in which they died. Like if they died right before a volcanic eruption and they're covered by ash, like a lot of the fossils in the United States are in a layer of ash material. But if there wasn't a specific sedimentation event that's going to cover up the fossils, then there's a good chance that the body would just decompose, and then there would be no fossil left behind. When we are looking at fossils or any layers of rock or material, we could judge the age of the material by using the law of superposition. And so this is a relative dating method, meaning it doesn't give us the exact date, but it will tell us what is older and which is younger based on the layer that it's at. So if we look at this cross-section of Earth, it's obviously not a real image, but if we look at this cross-section, we could see that the layers that were laid down first are going to be the oldest. So it's just like if you were to have, let's say, in your room you have a pile of papers or something like that. The older the papers are, the more toward the bottom of the pile they're going to be, and then the newer, the more recent the papers, the more closer to the top they're going to be. And so that's the same way with the Earth and deposition. The newer layers are the youngest layers, and the oldest layers are going to be at the bottom. And so places like the Grand Canyon, you could see just billions of years of history just in the cliff face. You can see the different types of rock and different material, and from approximately what time period each layer is from. So I actually went to the Grand Canyon this past summer, and they sell these posters and they label every single layer. And geologists go to places like the Grand Canyon and Zion National Park, and they analyze these rock layers, and they can kind of see, learn about different things by studying those rocks. Sometimes learning about or using the law of superposition, it's a little bit more complex than just looking at layers of deposition, because there are other things. There are metamorphic processes, and there's tectonic processes that occur that are going to alter the layers. So here's a simple graphic, and we could see that we have this layer C, this layer of shale is laid down, and then there's a layer of limestone, and then there's a layer of sandstone. And so we must have had layer C layered first, then B, then A, and then this intrusion, metamorphic intrusion from the mantle, D, must have intruded on all those layers. And we know that D came later because it's cutting through layers C and B and A. And if those layers weren't there, then the intrusion wouldn't be able to go through them. So we know that the order was C, B, A, D, and then the last thing was E, which is this slip fault, and so, or a strike fault. And this fault, we know it came last because it adjusts the layers of everything shown. So it adjusts C and B and A. They're downward on this side, and even the intrusion is slipped downward. And so therefore we know that that strike E, that fault had to have happened last. And then a geologist could look at a picture like this and determine what happened at what time. And so we could see that this intrusion A must have happened before the deposition of N and K and B, which were then tilted, and then we had a deposition of F. And so you could look at layers like that, and you could see exactly what's occurring. And you might say, oh, well, does this really actually happen? Do we have tilted layers of Earth? And the answer is yes. Here's an example of, this is in Castle Rock, west central Kansas, and we can see a very clear fault line where we have the layers displaced. So that's a very good example. Here's another one where we have, this is near Denver, Colorado. This is the highway cut, and we could see that the whole layer has been tilted. And so they think that this had something to do with the uplift of the Rocky Mountains. So as the plates collided and the layers went up, you can kind of see that the layers become tilted like that. And so that's how different layers can be adjusted. It's a lot more than just sedimentation. And so that's all relative dating, seeing which is older, which is younger. We could also get more precise dates through radiometric dating. And so the way radiometric dating works, you'll learn more about this in chemistry class next year, but the way radiometric dating works is there are certain isotopes, certain types of atoms that they're going to decay into other types of atoms, and they do that at a very predictable rate. And so we could take a sample of, let's say, carbon-14. Carbon-14 is going to what we call decay or transmutate into nitrogen-14 over a set period of time. And so if we analyze a sample of once organic material and we can see the portion of carbon-14 to nitrogen-14, we can get a pretty good estimate of how old that sample is. And then carbon-14 is a radiometric isotope that we use to date newer material, but we have different types, we have a whole set of isotopes that we use depending on the approximate age of the material. For example, we've dated the Earth with zircon crystals that had samples of uranium that decays at a known rate. And so by analyzing the portions of these radiometric materials, we can get approximate dates from analyzing the materials rather than relying on the relative data. And what's nice is we do these radiometric tests, and all those dates match up with the relative dating. And then also, in addition to that, what I didn't mention on a couple previous slides ago was we could use different specimens of fossils to determine the approximate age. And so let's say that we have a certain type of fossil that's found in one layer, and then we date the material and we find out that it's 350 million years old. Well, if we find that fossil somewhere else, then that gives us a good idea that that layer in a different location is about the same age. And so that's how we date materials globally. Let's go back to where we were. Okay, this is the geologic time scale. And so this is a lot to look at. The geologic time scale is a model that expresses the major geological and biological events in Earth's history. And so we can separate geologic time into eons, are the broadest categories. And so if you look closely at this, we have the Precambrian eon came first, and then the Phanerozoic eon came second. Anything that's Proterozoic and before, we just call Precambrian, because Cambrian is the Cambrian period is when most life started to show up. And so anything that's Precambrian, it's going to be very simple life forms, nothing complex. And so we call it the Precambrian time. And then after that is the Phanerozoic, or the age of life. And so the next smaller unit are going to be eras. So we can split the Phanerozoic into three eras. The Paleozoic is the oldest of the three in the Phanerozoic. Then we have the Mesozoic, and then the Cenozoic. And then we could take each era and we could split it down into periods, and then from periods to epochs. So for example, if we were to look at the Cenozoic, we could see that we could split it down. So we have the eon is the Phanerozoic, the era is the Cenozoic, the period is the Quaternary, the Neogene, and the Paleogene. Then we have the different epochs, for which we are in the Holocene right now. Humans showed up in the Pleistocene. And so if sometimes you need an analogy to put things into perspective. So remember, Earth is 4.6 billion years old. So if we were to take a string that was 4.6 meters long, humans didn't show up until the very tip of the end of the string. That's how old the Earth is, and that's how small of a time that we've been here on Earth. And so sometimes it's hard to put things into perspective. Throughout geologic history, there's been a lot of changes in the amount of species on Earth. And so what this graph shows is it shows us the number of families and how it's changed over time. And so you should know that this graph starts at 550 million years ago, and it goes from left to right to current times. And so we have the reason why we're not starting at 4.6 billion years ago is because for the most of geologic history, there wasn't anything alive on Earth. And so it took a long time for those species to eventually evolve to and then speciate to the point where we could start increasing in species. And so if you look closely at this graph, there are 5 major extinction events shown by circles. We have the Ordovician-Silurian event, we have the late Devonian event, we have the Permian-Triassic, which is the biggest extinction event in history, we have the Triassic-Jurassic, and then the Cretaceous-Tertiary, and then a lot of scientists cite right now as the biggest extinction event in history. And so all these extinction events, they correlate with either a rapid cooling of Earth's temperature or a rapid heating of Earth's temperature. All of them except for the Triassic, Jurassic, the Cretaceous Tertiary right here. All of them are associated with heating or cooling events, except for the Cretaceous Tertiary. This one is associated with an asteroid impact that created a nuclear winter type scenario that made it so that the amount of sunlight getting to the Earth's surface was significantly decreased, and that really had a negative effect on our environment. So I'm going to take you through each of the different eras. And so the first one, we're just going to call it the Precambrian. This is the first 4 billion years of Earth's history. So remember, Earth's history is 4.6 billion. So this represents 90% of Earth's history. So life first appears during the Precambrian. Autotrophic prokaryotes enriched the atmosphere with oxygen. Remember, molecular oxygen didn't exist on Earth for a long period of time, for 90% of Earth's history, until life forms, photosynthesizers, put it there. So eukaryotes emerged, the first animals appeared, and then food chains were very general and short and simple, because this is when life first started evolving. Look how many species we have. We have so few species during this time, during the Precambrian. Okay, and so the ecosystems had to be very simplistic. The next time era is the Phanerozoic. Phanerozoic is split into the periods of the Cambrian, the Ordovician, Silurian, Devonian, Carboniferous, and the Permian. So the ancestors of most major animal groups diversified in what the scientists call the Cambrian explosion. This is where most life, most body forms of life originated or started here. So first life on Earth, or first life on land, emerged during this era, and then this ended in a mass extinction during the Paleozoic. Is what ended. At the end of the Paleozoic was ended by the Great Dying, the biggest mass extinction in the history of Earth. And then the next era is the Mesozoic. And then so this has the Triassic, Jurassic, and Cretaceous periods. There was two major extinction events during this era, and the extinction event that ends this era is the one that we're all familiar with the asteroid that eliminated the dinosaurs. So dinosaurs, birds, mammals evolved during the Mesozoic. The KT boundary, or the Cretaceous Tertiary boundary, is a layer of material in between the rocks of the Cretaceous and Paleogene periods. It has an unusually high level of iridium, and what that suggests to us is that there was an asteroid strike. So asteroids can be high in iridium levels. Since iridium is rare on Earth, it's very likely that that's what happened. And so the meteorite impact changed the climate on Earth, wiped out the dinosaurs, and then many marine invertebrates and many plant species were all wiped out at this time. And that brings us to the current era, the Cenozoic era. So the Cenozoic era starts with that last major extinction. We can split the Cenozoic into the Paleogene, Neogene, and Quaternary periods, of which we are in the current epoch, the Holocene, where it's the epoch for us as humans. During the Mesozoic era, so not the Cenozoic, but the one shown in green here, this is when there's a lot of continental shifting activity. So over the course of 200 to 300 million years, we see that the continent shifted greatly. And the continent shifted because we have subduction zones where we have some continental plates going under other ones, thus making the oceans smaller. And then we also have ocean floor spreading, where we have divergent zones where the continental plates are diverging apart. I'll upload a video for you guys to watch on how this works. But basically, the study of the continental plates moving around is called plate tectonics. And so we could watch a quick animation on how this occurs. And so if you I've taken this video off of YouTube, and what I did is I reversed it and then I sped it up so it wasn't a 4-minute video. But if you look, mainly look, you'll see what areas are land and which are ocean, but look at the difference between the yellow land and then the orange mountains, because as these continents collide, that's what causes the mountains to arise. Because when you have those continental plates coming together, they are going to form mountains, and so when they collide, they form mountains. Okay, so look for that in this animation. So that's it for this section, and I hope you learned something cool.